Hello there, this is an Algebra 2 video. It is Chapter 3, Section 3, and today we will be learning how to optimize with linear programming. So there are some vocabulary that we're going to want to you're going to want to familiarize yourself with, but I'm going to go ahead and start the example and then talk about those different things as we go through the problem. So here it says, graph the system of inequalities, name the coordinates of the vertices. So that's where there's one vocab word, vertices, of the feasible region, another vocab word. And then it says, find the maximum and minimum values of the function for this region. So the first thing I want to show you is that over here we have what we call constraints or boundary lines. We're going to graph all these lines together and we're going to end up with what we call a feasible region, which is basically all the region where all of the shading takes place. So we've done graphing before and we've shaded before in the previous lesson. So now we're just going to be calling the region that is common into all three equations the feasible region. And the vertices are basically the corners of that region. And again, when we graph it, it'll make more sense. Secondly, I wanted to point out that it says find the max and min values of the function. This function down here might look a little funky to you, because it has two variables in there, but this is just function notation for an equation that has two variables. So my equation has x and y in it. So we just read that as f of x and y equals 4x minus 2y. And this function right here is basically the optimization equation, if you will. You do not graph this line. You only graph these three here. Once you get to the function notation here, that's what we're going to use for the max and min values later to optimize. When you're optimizing, you're either trying to optimize profit or minimize cost in most scenarios. But right now we don't really have a word problem attached to the example. We're just going to show you how to do it. So the first part is going to be pretty simple because we already know how to graph. We talked about graphing equations like this first one. That really just means that the y values are between 3 and 6. So we don't want any other y values. Whenever you graph a line like that that has no x variable in it, those are just going to be two horizontal lines at 3 and 6. So I'm going to come over to my board. And here's about 3, 4, 5, and here's 6. So I'm just going to go ahead and graph a horizontal line at 3 and another one at 6. And because we know that we want to be between 3 and 6, at this point we are graphing or shading above and below those two boundaries. Then we have another line and it's 3x plus 12, and that's in y equals mx plus b form. So over here is my y-intercept of 12. And it says 3x is the slope. So one option that I have is to go up 3, right 1. But as you can see, I'm going to very quickly be off of my graph. So I actually want to do that. Instead of going up and right, I'm going to go down and left to do this. So 1, 2, 3 over 1. Then 1, 2, 3 over 1. Right about there. Okay, so let's put those dots together. Right about there. And there's my third line. And so you'll see that I went 1, 2, 3 down and over 1. And then I went 3 more down and over 1. And then 3 more down and over 1, just to make sure that my line was nice and straight. And then we have our next equation, which is also an mx plus b, negative 2x plus 6. And 6 is right here, as we said earlier. That's 1, 2, 3, 4, 5, 6. And the slope now is down 2 over 1. So down 2 to the right 1, down 2 to the right 1, and then down to right 1. So it should be right about there. I like to use the slope more than once to just guarantee that my graph is as accurate as I can make it. That is important when you're doing these kinds of graphing problems. Okay, so now I've graphed all of these lines, and I need to do the shading for the red and the orange line. This one says less than or equal to, so really quickly you can test the origin, which is right about here. And if I plug in 0, I'm going to get that 0 is less than or equal to 6. And 0 is in fact less than or equal to 6. So we want to shade towards the origin. And for the second line, we have, if we plug in 0, that y is less than, or sorry, that 0 is less than 12, which is also true. So we're going to shade that direction. And so basically what you're going to end up with is this region that is basically below this blue line, above the bottom blue line, and in between the red and orange line. So you have this funky looking trapezoid in here. Okay, so that's the first part of what they've asked us to do, is to graph the inequalities. Now they want us to name the coordinates of the vertices. So we need to find, oops, sorry about that. We need to find the coordinates of these 4 points of this region. So just to talk about the vocab again, the vertices refers to the corners where the lines cross for the region. Obviously the lines cross here as well, but that's not part of the feasible region. And of course the feasible region is the part that we shaded. So this is my feasible region. It's a trapezoid, and I've got 1, 2, 3, 4 different vertices, and I need to name those right now. So I am going to do that. And we have this point on the top left is -1, -2. So x is -2. And then the y value is 6. We also have over here -1 and -3, 3. And then over here on the right, we have 0, 6. And then on the bottom right, we have 1, 2, so 2, 3. So this guy is down 2 over 1, down 2 over 1, down 2 over 1. Yeah. So those are our vertices for this example. Let me see, make sure I got a -3, 3, 0, 6, -2, 6, 1.53. So according to the book, this point 2, 3 is actually 1.53. I'm trying to see there. That would be this line 6, down 2 over 1, and then down 2 over 1, and down 2 over 1. So apparently this point is actually in between 1 and 2. So this last point that I put up here, 2, 3, is actually 1.53. And you can always confirm that with algebra. Right now, in the interest of time, I'm just going to keep going. But the next step of this problem is to find the max and min values of the function for the region. So that would be the bottom one here. That's our optimization function. So what we're going to do is we're going to plug in each of these vertices into that function and see which one of those vertices gives us the maximum value and which one gives us the minimum value. So to do that, we're going to do f of xy. F of, which literally means to take 4 times -2 minus 2 times y. 4 times -3 minus 2 times 3. 4 times 0 minus 2 times 6. And 4 times 1.5 minus 2 times 3. So all I've done is I've taken the 4x minus 2y, so 4x minus 2y, 4x minus 2y, 4x minus 2y, 4x minus 2y. In each case, I've replaced the x variable with the negative, with the x coordinate of the point, -2, -3, 0, and 1.5. And in each case, I've replaced the y variable with the y coordinate. So 6, 3, 6, and 3. All right, and to see which one of those gives us the biggest value. So 4 times negative 2 is negative 8, and negative 2 times 6 is negative 12. So we get negative 20 up here. And for the second one, we're going to get negative 12. 4 times negative 3 is negative 12, and then 2 times 3 is negative 6. And that's going to give you negative 18. And then we're going to have 4 times 0 is 0, negative 2 times 6 is negative 12. So 0 minus 12, we're going to get negative 12. And then the last one, 4 times 1.5 is going to be 6. Minus 6 is going to give us a 0. Excuse me. So, sorry about that, my little alarm went off. But anywho, so we get those values and we get negative 18, negative 20, 0, negative 12. Okay, so what we want to do now is which one of those values is the biggest and which one is the smallest. So the smallest is not 0 because negative numbers are smaller than actual 0. So actually 0 is the biggest number here because it's the only positive, or it's the only number that's not negative. So automatically we will say that this guy right here is our maximum. And they wanted to know, find the maximum minimum value. So the maximum value is 0, and the minimum value is the biggest negative, and the biggest negative is up here, negative 20. So the maximum value is 0, and the minimum value is negative 20. And that is how you do optimization with linear programming. So now I'm going to ask you to do 2. This is just the first of 2. Do it yourself, number 1, part A. I left it only 1 to a screen because you're going to need all of the space so that, I'm going to need all the space to explain it later. And then here's do it yourself part B. And then we're going to move on to example 2, which is pretty much the same thing, but what we call a unbounded region. So pardon me while I get my stuff together here. Don't mind me. Okay, so sorry about that. So we're going to do this one in much the same way. The difference with this example and the previous one is that this one has what we call an unbounded region. That means a region where the lines don't cross. But again, as we see the graph, you'll see what I'm talking about. But in the beginning, again, like I said before, we're going to graph these 3 inequalities here. We're not going to graph the 4th one. That's going to be for later for the max and min values. The directions, by the way, for example 2 are the same as example 1. I just didn't want to write out all of the directions because it was just going to take too long. So hopefully that makes sense. So right now what I want to do is graph. And so the first equation is what we call standard form. So I want to go ahead and do that first. So I'm going to get if x is 0, then y is going to be negative 12 divided by 2, which is negative 6. And then if y is 0, then I'm going to get x equal to negative 12 divided by 3, which is negative 4. So I'm going to graph that equation with that guy. And then I will come to the second one. So here we're going to go 0, negative 6. So x is 0, y is negative 6 right here. And then negative 4 zeros, 1, 2, 3, negative 4 zeros right there. We're going to graph our line. We're going to test the origin to see which direction we're going to shade. And so if we plug in 0, 0, we're going to get that 0 is larger than negative 12, which is true. So we're going to shade towards the origin. And then I'm going to go to the next equation, which is 3x plus 12. And one thing that I wanted to show you is that the 3x plus 12 is way off my graph because, as you know, with y equals mx, we have to plot the 12 first. But my graph only goes to 4. So I wanted to show you what you could do in that case is to use a t-table really quick and just evaluate for a different point. For example, you could evaluate for a negative value, for example. The reason why I'm not going to pick a positive value is because if I plug in 0, 3 times 0 is going to be 0 plus 12, but as I said, I don't have 12 on my, the y variable 12 is not on my graph. If I plug in a 1, then I'm going to get 15. So if I put positive numbers, this y value is just going to keep getting bigger and bigger. But I want smaller y values. So I'm going to do something like maybe -2. And 3 times -2 is -6. And 12 minus 6 is 6. And that's something that's a little bit easier for me to graph. Maybe even a -3. So 3 times -3 is -9. And 12 minus 9 is +3. So I'm going to use those 2 points instead of y equals mx plus b to graph this because I don't have enough space. So -2 is here, and then this is 4, so 5, 6 is going to be like roughly about here. So I'm going to go like that. Maybe I should try -4 because I don't have enough space for that one either. So -4 would be 0. So instead of using -2, 6, which is also off my graph, I'm going to go ahead and use -3, 3. So here's 1, 2, 3, 1, 2, 3 right about there. And I'm also going to use -4, 0, which is right here. And then I'm going to graph the points this way. So just a little trick for you if y equals mx plus b is not going to fit on your graph. You could also make the graph bigger, but as you can see, I don't really have an option for that right now. So just want to say again, -4, 3 times -4 is -12, -12 plus 12 is 0. So that's where I got those values from. If I test the origin to know which way to shade, I'm going to get 0 is smaller than 12, which is true. So again, we're going to shade towards the origin. And then my last line is 3x minus 6, and this one's actually feasible on my graph. I'm going to do -6 as my y-intercept. And then we're going to go up 3 over 1, so we'll go 1, 2, 3 over 1, and then go 1, 2, 3 over 1. And I'm going to get my graph like so. And again, we're going to be checking the origin. If I plug in 0, 0, I'm going to get a statement that says 0 is larger than -6, and 0 is larger than -6. So towards the origin we go. And my shaded area is here. What I wanted to show you is with this example is that it is possible to get a feasible region that is unbounded, meaning there's no, at the top end here, there's no boundary line that's coming across this direction. But we still have some vertices. We have one here. Oops. We have this one here, and we have this one there. So in this case, we only have 2 vertices. This one is going to be -4, 0. And this one's going to be 0, -6. And so we plug them into our function. And this time our function is 9x minus 6 times y. So we're going to get 9 times -4 is -36. And 6 times 0 is 0. And 9 times 0 is 0. And here we're going to get +36. So in the first case, we're going to end up with -36. And in the second one, we're going to end up with +36. All right? And so the question was for us to find the maximum and minimum values for the function. So the maximum value is +36, which occurs at 0, -6. And there's no minimum value. And the reason for that is because it's unbounded. So -4, 0 is over here. But there are other values in the region that actually yield smaller values than -36 because of the unboundedness. So that's basically how you do that, little guy. So again, we're going to deal with do-it-yourself number 2, part A. And then here is part B. And then I'm going to do one more example for you. This one's more of a word problem. I know you guys don't like word problems, but I'm going to hopefully try to walk you through this one so you're not as confused. So here we go. It says, each week Mackenzie can make 10 to 25 necklaces and 15 to 40 pairs of earrings. So one of the first things we want to do is recognize that we're dealing with two different things, hence the two variables. We've got necklaces, which we can just call X, and we've got earrings, which we can just call Y. Now based on that, we know that for necklaces, they're going to be between 10 and 25. So there's my equation right there for the X's. And then we have 15 to 40 pairs of earrings. So we're going to have 15 to 40 pairs of earrings. And it says if she earns profits of $3 on each pair of earrings, so that's our function, that's our profit equation. Our function xy is going to be $3 for each pair of earrings, which is y. And she's going to earn $5 for each necklace, which is x. Make sure the variable is attached to the right thing. And she plans to sell at least 30 pieces of jewelry, which means combining the earrings and the necklaces. So x plus y, she wants to sell at least 30 pieces, which means greater than or equal to 30. That's the hard part, is trying to get together all of the equations that you need. Graphing it now will be very similar to what we've been doing already in the previous examples. So, because I know that it doesn't make any sense to have negative values when you're talking about items, like how would you talk about having negative pairs of earrings? Doesn't make any sense. So I'm going to go ahead and just use the positive quadrant for my graph. And we've got numbers like 10, 15, and 30 going on. So I'm going to go maybe by fives. So I'm going to go 5, 10, 15, 20, 25, 30, 35. Same thing for the X. 5, 10, 15, 20, 25, 30. Okay? So, this is Y over here. Alrighty, so to graph this guy, we'll start with the first one. And again, remember what I said before, when you don't have any Y variable, these are just vertical lines between 10 and 25. So vertical lines is 5, 10, so this is going to be my 10 right here. So I'm going to go ahead and graph 10. Okay, come on. I don't know why it's not. There we go. There's 10. And then 25 is over here. Let's try to make that as straight as possible. Okay. So there's between 5, 10, 15, 20, 25. And of course we want to go in between them. And then for Y we're going to be between 15 and 40. So 5, 10, 15. So here's 15. And then we want to do 40, and 40 is going to be roughly up here somewhere. I should have got a little further on my y-axis and I didn't, so I apologize. But we'll fix that right now, real quick like. Okay, just like that. And of course we want to be between those as well. So right now we're in this little rectangle. And then the last equation we need to graph is the x plus y 30. And of course that's in standard form. It means that if x is 0, then y is 30. And if y is 0, x is 30. So that one's nice and easy. So we're going to go 0, 30, and 30, 0. And try to connect those two together, see if my ruler will reach. Oh, it's barely going to make it. Something like that. And for that guy, is 0 bigger than 30? Yes, it is. So, sorry. If I plug in 0, 0 here to check the origin, I'm saying that 0 is larger than 30. That's not true. So you don't want to shade toward the origin. You want to shade this direction. So you end up, okay, you end up in this region right here. It's a little funky there. Coolness. Like that. And then you have your vertices here. Why do I keep doing that? I don't want the highlighter anymore. We've got that guy, this guy, this guy, this guy, and this guy. Okay, so we want all those values. So I need to make some space over here. And our values are going to be, starting with this guy, this is going to be x value is 10, y value is 40. Right over here we're going to have x value is 25, and the y value is 40. And then for this guy we're going to get x value is 25, but the y value will be 15. And then for this guy we're going to get 5, 10, 15, and 15. And the last vertex is going to be 5, 10, and 20. Those are my vertices. And then I just need to plug them into my function, which is 3y plus 5x. So that's kind of backwards from what we're used to. So I'm going to go ahead and put 5x first. So 5 times 10 plus 3 times y. 5 times 25 plus 3 times 40. And 5 times 25 plus 3 times 15. And 5 times 15 plus 3 times 15. And lastly, 5 times 10 plus 3 times 20. Okay, so we've got 10, 40, 10, 40, 25, 40, 25, 15, 15, 15, and 10, 20. Make sure that's all right. So 5 times 10 is 50. And 3 times 4 is 3 times 40 is 120. So 120 and 50 is going to give you a whopping 170. So this is going to give us 170. The second one's going to give us 5 times 25 is 125. And 3 times 40 again is 120. And together that's going to give you 245. And then we have 5 times 25 is again 125. And 3 times 15 is 45. And 125 and 45 is going to be 170, I believe. Yes, 40, 50, 60, 70, 170. So these two are going to give you the same amount for profits. And then 5 times 15 is going to be, let's see, 75. And 3 times 15 is 45. And 70 and 40 is going to be 110. 110 and 10 is 120. And then lastly we get 50 plus 60, which is also going to give us 110. All right, so these are all the vertices, and so when it says here, how can she maximize her profit? Her maximum profit is going to come from the $245 right here. That was the biggest number that we had, 245. And that means that X, which was necklaces, she will have to sell 25 necklaces and 40 pairs of earrings. And if she does that, then she will maximize her profits at $245. And that is how you do that. And I didn't give you a do-it-yourself question for this last one. So thank me later. But once you have finished taking your notes and doing the do-it-yourself questions from before, then you will have completed your notes for this lesson, and I will see you in class, and thank you for watching.